Welcome, dear learners. This is the second lecture on the series of MOS Capacitor. In the beginning course, you have learned about the different conditions and the application of biases. You know the accumulation, depletion, inversion. I think all the band diagrams are described in more details and how those things appear and etc. Today in lecture 2 and in the next lecture, lecture 3, I will go for the electrical characteristics of the MOS capacitor. And once this electrical characterization will be finished, then I will go to lecture 4, 5 and 6, which will be derived from the first 3 lectures, and that will discuss about the MOSFET. So all the details of MOSFET, from its electrical characteristics to circuit design to say short channel effects and etc, all these things will be discussed. Myself, Arpan Deashi from the Department of Electronics and Communication Engineering in RCC Institute of Information Technology, India. Welcome all the learners to the second lecture in the lecture series of MOS and MOSFET. So, good morning to all, and I think I have just to mention the prerequisite for going to the lecture 2 before moving towards the details. And what are the points should be exactly mentioned? If I just recall or make a slight sort of recapitulation in our earlier class, so it will be, we have discussed the formation of band in a MOS structure under unbiased condition, if you know. And before that, I have discussed how the homostructure and heterostructure, both the things, how these are formed. And if you remember, I said that Fermi level will be considered as a reference level for homostructure design, as whereas for a heterostructure, we have to consider the vacuum level as the reference level. And that is basically called the Anderson's rule. And based on the Anderson's rule, I have shown the unbiased condition band diagram for a MOS structure. And if you recall, I have said that there are two types of things are possible. One is for p-type silicon, another is for n-type silicon, because we have chosen aluminum silicon dioxide silicon as our conventional material composition to discuss the preliminary levels of the MOS. So silicon may be p-type and silicon may be n-type. And in the earlier lecture, I have considered all the variations of the band diagram for p-type substrate. We can call it also n-type substrate, so the band diagram will be reversed in different cases. And you also remember that we have shown the variation of the band diagram if metal voltage is less than 0 for this system, that means aluminum silicon dioxide silicon P system. If metal voltage is less than 0, then we consider the case as accumulation. If metal voltage is greater than 0 but small, we call it as a depletion. Whereas if metal voltage is much greater than 0, then we consider as inversion. And what is the inversion condition, if you remember? At that criteria, the intrinsic Fermi level bends in such a radius of curvature that it crosses the extrinsic Fermi level. So that's the difference basically in terms of the Fermi level. And I have also said that both conduction, valence and intrinsic Fermi level will bend with the same radius of curvature. So that's one of the key point while we are going for the calculation of this MOS structure so far. And before going to further mathematical details, I want to make one very key point regarding the calculation. That's the factor that in our system we will set some convention and we set some symbols also, which will be totally followed in all the 6 lecture courses. Maybe it may be 7 to 6 to 7. So what I have found in my real-time experience of delivering lecture in the physical classroom, that students tries to consult with different books and they will find different symbols, and then there will be a problem with that and they have some geoparadized and don't know how to be solved this thing, and ultimately they made some wrong answers. And not only the wrong answers, the numerical problems, they also give some wrong results, and especially in terms of signs. So there is a major problem. So So what I want to refer before beginning of the lecture 2 is that I will set a particular convention of the band bending, and it will be followed throughout all the series of lectures of MOS and MOSFET, as well as I will consider aluminum silicon dioxide silicon P system. That's my second point throughout the discussion. And third, I will make the one set of symbol for all the derivations of MOS capacitor and MOSFET, so that you can understand these things quite easily. And I will go with a little bit slower pace, because from now on today, in this lecture and the next lecture, we have a lot of mathematical equations. So I will make some pause so that if required, you can write down the mathematical equations and you can progress. Obviously, the lecture will be available in my YouTube channel, so at any time you can make the pause in the internet on condition, and you can write down the equations, match with your own derivations, and find out is there any discrepancy or not, and you can progress in that way. But I am showing the equations, all the equations, in a slide with a greater font, so that you can understand what are the terminologies, how mathematical steps are going on. And generally, I am trying to follow or incorporate most of the mathematical steps in my derivation, so that you can get a good look and good approximation related to these factors. So with this small introduction, what I am saying, I have to go to the details of this MOS capacitor mathematical analysis. So for that part, I start with the recapitulation of the inversion condition. So you know that inversion condition for aluminum silicon dioxide silicon P system is valid if metal side voltage is greater than 0 and large. I think this condition is previously discussed. So this is my metal, that is called aluminum. Then I will come to the silicon dioxide band. Now again, for recapitulation, I want to mention a few factors. You should please consider it, because it will be extremely useful once I am going to the details of mathematics and drawing the physical inferences from this mathematics. The positive voltage is applied to the metal side. Please think. So if that is applied, that means electrons are basically pulled down in the metal side. So the Fermi level of the metal side will go downwards naturally. Now you are applying negative voltage at the semiconductor side. So if you apply negative voltage at the semiconductor side, then electrons, which are the minority carriers in the p-type substrate, they will be repelled. And if you repel the carriers, then these carriers will try to move towards the metal side. But it can't reach to the metal due to the presence of the insulating layer. So most of the minority carriers will be accumulated in the insulator semiconductor interface or insulator substrate interface. So insulator substrate interface, that region will be slightly less p-type because of the accumulation of minority carriers. Now you know that if it is slightly less p, then the gap between extrinsic Fermi level and the conduction band reduces than that of actually the case of normal p-type semiconductor. Now we know that our convention is the extrinsic Fermi level will remain constant throughout a particular material. So in order to reduce the distance, we have to bend the conduction band downwards. And if we bend conduction band downwards as shown in the figure, then the valence band, that will bend downwards, and the intrinsic Fermi level will also bend downwards. You may ask why valence band will bend downwards? Because by application of bias, we can't change the band gap of a semiconductor. So if conduction band bend downwards with a particular radius of curvature, then the valence band will also bend downwards with the same radius of curvature. And what is the definition of intrinsic Fermi level? It in generally lies very close to the middle line of forbidden region, that means between the conduction and valence band. So by application of bias, you can't also change the distance between intrinsic Fermi level to conduction or to valence band. So if valence and conduction band bends with a particular radius of curvature, then the intrinsic Fermi level will also bend with the same radius of curvature in the same direction. So that's the bending of the band diagram. And how inversion is reached? Inversion condition is reached if the intrinsic Fermi level crosses the extrinsic Fermi level after bending. That means we have to reach the case of point of inversion. Why? Because if we have to invert p layer, it should become n layer. Naturally, we have two types of doping. So for n layer, after conduction band, if we move vertically downwards, after conduction band, there will be extrinsic Fermi, then there will be intrinsic Fermi, and then there will be valence band. So that concept is depicted in the region very close to the insulator semiconductor interface, and that's why it will be called as the region of inversion. And the point of inversion, and I am going to that, and also we know that the difference, energy difference, better to say, between intrinsic and extrinsic Fermi level is called Fermi potential. So the energy difference should be measured when they are parallel to each other, that means in the bulk region. And that's why I am showing the Fermi potential, that means the bulk region, in your diagram, which is shown as a double arrow with a pink color, and it's written as psi f. So what is psi f? Psi f basically measures the difference when it is at bulk, because we consider it's a simple 1D approximation of the band diagram and the bands are straight line. Once we go for 2D, 3D, those cases, then we have to consider the exact shape of the bands, and I'm not going into that at the right now point. I have just considered that it will be somehow better if we consider these things. So that's fine. We have no problem with that. And last part, why insulator band diagram is tilted so far? Because these magnetic areas which are accumulated at the insulator semiconductor interface, you have to restrict them to go to the actual metal layer. So what you have to make, you have to virtually raise the potential barrier at that side so that these carriers can't basically go towards the metal side, and that's why you have to raise the potential barrier at that interface, and naturally it will be tilted towards the metal side. It will make an inclined plane. So that's the insulator band diagram. I am again explaining this, just a recapitulation, but that concept of inversion should be made very clear once we are going into the more details. Then I am going to express the another potential which I have already explained, but let it go in a deeper sense. That is called the surface potential. Now the question is, what will be surface potential? Surface potential is measured at the total bending of intrinsic Fermi level by virtue of applied bias. Again I am repeating, please remind, surface potential is the total bending of intrinsic Fermi level due to the external bias applied in the structure. Now, where you will get the total bending? That means the total bending should be measured obviously at the insulator substrate interface. So it is shown as by the two green dotted lines, which one is giving the point where the intrinsic Fermi level meets the interface, and second is the reference line, which is the actual value of the intrinsic Fermi level at the bulk. So that will give you the total bending of this level, and that is known basically as the surface potential, denoted by psi s. So from that point, I think it is very clear to understandable for all of you that surface potential is less than Fermi potential for both accumulation as well as depletion. If you go to the point of inversion, then surface potential becomes equal to the Fermi potential, which is shown in the blue color oval shape, which is given where the intersection occurs. But if intrinsic Fermi level crosses the extrinsic Fermi level and denotes the inversion condition, then surface potential becomes greater than the Fermi potential. So three possibilities better to say are possible. Again I am repeating, Surface potential is less than Fermi potential for accumulation and depletion, because in either of the cases, generally yeah, it can't cross the extrinsic Fermi. In accumulation also, the band bending is in the reverse direction, so surface potential becomes negative. Naturally, if you measure downwards, if it is a positive quantity, if you assume, then measuring upwards will be a negative quantity. It's a very simple thing, so I'm not going into that details. But so surface potential is negative, so at that case there is no comparison possible. For depletion, surface potential is less than Fermi. For point of inversion, surface potential is equals to Fermi, and once inversion occurs, surface potential is greater than the Fermi potential. And I am showing some green bubbles which are in the conduction band of the substrate, and that basically the accumulation of the minority carriers. So that basically depicts the inversion condition. Now, I am trying to go for the classification of inversion. Look the figure very closely. In that case, extrinsic Fermi level and intrinsic Fermi level, they have a crossover. Intrinsic Fermi level goes below the extrinsic Fermi level. It's fine. But if you introspect that region more closely, the gap between intrinsic and extrinsic Fermi, I am repeating again, the gap between intrinsic and extrinsic Fermi at the bulk is greater than the energy gap after crossover. That means the value of psi f, which is achieved at the bulk condition, that value is greater than the difference of the Fermi levels after crossover. That means psi f is greater than psi f, but psi s is less than 2 psi f. So that means surface potential can't become equal to the twice of the Fermi potential. So that is one of the very important aspect, and if that situation happens, then it will be called weak inversion condition. So after depletion, we come to the case of point of inversion. After point of inversion, the intrinsic Fermi level bends further, goes below extrinsic Fermi level, but the bending after or the movement after the crossover is not the energy gap which is at the bulk condition. So it will be psi f plus some small quantity psi, where the psi is less than psi f. So psi s, that means the surface potential, is less than twice of Fermi potential. That condition is known as weak inversion condition. I am repeating again, that condition is known as weak inversion condition. But now look at the figure. The intrinsic Fermi level crosses extrinsic Fermi as usual, because that's the inversion condition. After crossover, it goes below the extrinsic Fermi, fine, and the energy gap between the Fermi levels after crossover may be equal to or greater than the energy gap with respect to bulk. That means after crossover, at the interface, the energy value may be psi f or greater than psi f. That is meant by the surface potential is greater than or equals to twice of Fermi potential, and that condition is known as strong inversion. So again, I am repeating this part in a vivid details, because in the derivation we have to classify the weak and strong inversion. The weak and strong inversion are the two types of inversion condition, where in the weak inversion, the surface potential is greater than Fermi potential but less than twice of the Fermi potential. Whereas under strong inversion condition, surface potential is greater than or at least equals to twice of the Fermi potential. So that's the difference comes in terms of band diagram, and that basically classifies the strong and weak inversion criteria in a MOS capacitor. So now instead of three types of classification, we have understood that there are four types of classification: accumulation, depletion, weak inversion, and strong inversion. So we have just slightly moved towards slightly more details. I will incorporate another condition a little bit later when I will go to the graphical explanation. So I think these concepts are clear. And if you look out these parts, I think so four conditions are cleared where in both weak and strong inversion, the voltage will be large, but there is a difference. How large? It basically quantitatively measured by the amount of bending of the intrinsic Fermi level. So that basically differentiates between the two types of inversion criteria. So up to that, I think I have cleared all the prerequisites in going towards the MOSFET. So better first MOS capacitor, and later it will be called as a MOSFET. So after this point, I am going to the mathematical formulation of the band bending. Now, our technique should be first understand the basic physics, represent the corresponding term by mathematics, and once mathematics is clear, to make a derivation. And our objective is not to derive, our objective is to find out the expression of the meaningful quantities which can be graphically represented or tabularly calculated, so that we can get a positive inference and we will know how this device will ultimately behave. So that will be the objective of the lectures now onwards, and we are moving towards that. Now, before going to the details of the derivation, let me first say what are the assumptions. The assumptions are very important, and we will follow these assumptions for this system throughout our series of the MOS and MOSFET lectures. Now, what are assumptions? If the potential bend downwards, then it will be called as positive. So, any downward bending of band will give you positive measurement of potential, whereas the upward bending of the band gives you negative measurement of potential. So please now think more clearly. If for accumulation condition for aluminum silicon dioxide silicon system, if you take accumulation condition, then the band bend upwards, that means the surface potential becomes negative. For depletion condition, weak inversion condition, and strong inversion condition, the band bends downwards, that means surface potential becomes positive. So these are very key points for the objective sort of questions as well as for clearing competitive exams. So you have to remind these assumptions, and now you start to classifying. So again, if you remind, the bending of the band and measurement of surface potential is quite analogous to your metal side voltage. If metal side voltage is negative, then it will be accumulation and surface potential is also negative. If metal side voltage is positive, then surface potential is also positive because band bend downwards, and it may be depletion, weak inversion, or strong inversion criteria. So that's the first part. Second, how band bending will be defined. Now, bending of the band at any point. Please think. Now, I can't measure always at the interface. So, at any point in the substrate, the bending of the band is the value minus the reference value. Now, what is the reference value? Reference value is in the bulk when all the bands are in parallel to each other. So, the potential is potential at any point minus potential at the reference value. And for EC, the reference will be conduction band. For EF will be EFI. So EV will be reference in the valence band as usual for descriptive cases. So that's the quantitative definition of the band bending, and that is the methodology to measure. And what are our boundary conditions? Naturally, if all bands are parallel to each other, you know the potential should be zero. There is no bending of the band, so potential is normally zero. But If you measure at the interface, then potential is surface potential that I have already shown in the last 3 slides. Now, for measurement, since it's a one-dimensional model, so for measurement, we will consider the variation will be along, say, particular axis, say z-axis. So where we should set the origin? We are setting origin at the semiconductor and insulator interface. Because I said that at that time the metal Fermi level fluctuation doesn't matter for our MOS capacitor detailed calculation, that will be considered in a later part. So I will show that animation with some description in a later part. But for the time being, we are mostly considered the right part from the substrate insulator interface towards the bulk of the semiconductor. So we consider the Z equals to 0 at that interface. So from that interface, if we move towards the semiconductor, the Z becomes positive. That means our linear scale becomes positive. If we move towards the insulator and towards the metal, the scale will be negative. So that's the basic consideration of the mathematical representation of band bending. Once we know this, we have to start to formulate it. And you know that most of the electrical characteristics are measured in terms of naturally the Poisson's equation. So we start with the Poisson's equation. Now, what is Poisson's equation? If I say in a language framework, Poisson's equation is the second order variation of potential related with the total charge density. Now, in a MOSFET, how could you measure the charge density? There are free charges, there are bound charges, there are donors, acceptors, majority carriers, minority carriers, everything. So, if we consider the substrate type, it will be P type. So, naturally, the free charge variations will be Pz minus Nz. And what will be the variations of the donor part? That will be ndz minus naz. So we are getting these variations. This will be total charge variations inside a bracket. So I think it's slightly okay, fine, that doesn't matter, but ultimately this will be the total charge variation. Now consider the bulk. In the bulk, you know that Pz equals to nothing but bulk substrate. So it will be the dopant concentration, acceptor concentration. It's very simple. So if you incorporate mass actions law, then you will get the value of Nz, and that will be Ni square by Na. I think it's very simple to calculate, so there will be no alternative or going on. So Nz equals to Ni square by Na. Now once you know that, I am starting to put the charge neutrality condition. You may ask why I am going for that. Because the system should be in stable equilibrium electrostatically. So one of the thermodynamic equilibrium will be always the electrostatic consideration also. So the total charge density should be equals to 0. So what will be the effective doped concentration? That means Nd minus Na. That will be Ni square by Na minus Na. Basically, I am substituting the value of P type and N type charge, and that I am getting. So if you get the value of this Nd minus Na from this side, so Ndz minus Naz, then you will get the value of Pz. Now comes to the case of charge variation. You know from your basic semiconductor physics, the Pz will be given, you know that Pz means the Fermi, extrinsic Fermi goes close to the valence band. So Pz will be the change of the Fermi level, that means psi f minus psi I stands for intrinsic, in the form of exponential function q by kt multiplied by the intrinsic concentration. Now psi I, what is psi I? Psi I is basically the potential at the inversion condition, but it can be made or measured at any generalized point. If you forget, I am showing you again the mathematical representation here, where I am considering psi z is psi I z minus psi I at z equals to infinity. And what is psi z equals to infinity? It is basically 0, because I have already said that in the first boundary condition psi z equals to 0 at bulk semiconductor. So if I put that, then psi I z is nothing but psi z. And if I substitute this, then I will get the value that it is given in the form of psi f minus psi into q by kt exponential form into ni. So once you will get that, you know exponential a minus b is exponential a into exponential minus b. So I am making just a simple mathematical logic. Now make it more closely this part which I have shown under a group. Ni exponential q psi f by kt. What it basically determines? Q psi f by kt is where psi f is measured. Psi f is measured at the bulk. So at the bulk, this exponential function multiplied by charge concentration. So what it will represent? It will represent the charge concentration at the bulk. So charge concentration at the bulk, what is the value? We have mentioned just 2 slides before. If you forget, I am showing here in bulk substrate Pz equals to Na. So if I substitute again here, then Ni exponential psi f q by kt will becomes equals to Na. Again, I am repeating, if you can't understand or if you have a slight misconception, please think this part very carefully. Exponential term, in what is the term inside bracket? Q psi f by kt. Where it is basically measured? Psi f is measured in the bulk. We have shown in all the inversion band diagram. So in the bulk, all the bands are parallel. Sorry to say, in the bulk, all the bands are parallel. So if all the bands are parallel, then what will be the concentration? If I multiply with Ni, what will be the effective concentration? Effective concentration at the bulk is Na, the acceptor concentration, because it is a p-type semiconductor. So Na exponential minus psi q by kt. Similarly, I am going to calculate for Nz. Nz is nothing but the donor, so extrinsic Fermi level goes upward, so it will be psi I minus psi f. Again, psi I becomes equals to psi, it is very clear, because it will be the upward shifting, and I am substituting psi z tends to infinity is 0. That's the first boundary condition and my band bending requirement. So once I am putting this, again this will be divided into two parts. Exponential a minus b is exponential a into exponential minus b. Again, look out the term Ni exponential minus psi f by kt. So what it will ultimately gives you? If psi f by kt, again it is measured, where it is measured? In the form of n-type n part. So where is the n part? N part is basically the minority concentration. So it is measured in the bulk but for the minority. Previously, the value is measured in the bulk but for the majority. Now it is measured in the bulk but for the minority. For the minority, what will be the value of it? It will be Ni square by Na. If you again forget it, I am showing the previous slide where I have written that in the bulk it will be Ni square by Na. So Ni square by Na is the minority carrier concentration at the bulk, and I am substituting the value of Ni square by Na multiplied by the less of the factors. So that will give you the value of Pz and Nz. Now once you know the charge variation, substitute all the values in your Poisson's equation. So d2 psi dz2 equals to minus q by epsilon, that's the normal factor, I am not going into that. The first term, Na exponential minus q psi by kt, which is nothing but Pz, minus Na, that is our original Na, minus Ni square by Na exponential psi q by kt, that is minus Nz term, plus Ni square by Na, this is basically nothing but our dopant concentration, which is Nd. So Nd minus Na, I am substituting Ni square by Na minus Na, that's very simple, and I am getting the values of Pz and Nz. So that's my reformulated Poisson's equation. Please try to understand this equation very clearly. This is my reformulated Poisson's equation after calculating the charge variation of Pz and Nz and also the values of the doped carrier concentration, effective doped carrier concentration, better to say, Ngz minus Naz. So once you will get all these values, the d2 psi dz2 in the Poisson's equation, look at the equation. The first two part I have written in that format. Why? The first two part you can take Na as common. In the second, third and fourth term, you can take Ni square by Na as common. So if you take all these parts are common, then what will happen? You just have to reformulate the equation and it will look like in this format. if you take Na as common, it will be e to the power minus q psi by kt minus 1. If you take Ni square by Na with a minus sign as common, it will be exponential q psi by kt minus 1. So what I am trying to take, that e to the power some function theta minus 1, that will be our term inside the bracket. The theta may be positive, theta may be negative, doesn't matter, but this will be our required formation in order to solve the Poisson's equation. So once I am getting this value, I am going for the solution of the Poisson's equation. Now you know that if you want to solve any differential equation, you require some boundary conditions. So we have to find out what are my boundary conditions. The first boundary condition I will come before going to that. Then our step will be that we have to integrate, because you end of the day you want electric field and charge. That's a very simple manner. You have to integrate from bulk to surface naturally, because you are moving in that direction. So at bulk psi equals to 0. At surface it is the value of d psi dz equals to 0. And you have to multiply both sides by d psi dz in order to solve it. Mind it, d psi dz is nothing but a negative value of electric field. That factor should be reminded once you are going for the solution of this equation. So we are going for this two-step methodology for solution, that we have to integrate from bulk to surface, and look, in that step the boundary values are given, that it will be a definite integral, so psi equals to 0 to d psi dz equals to 0. And once I am considering this, I have substituted the value of 0 to d psi dz, both sides. So actually in that format, but later it will be modified, because once I am going for some calculation, the both sides will be changed. So actually the right hand side will be slightly modified. It will ultimately goes from 0 to psi, because the function is nothing but a psi variation. So once I am trying to calculate it, it will be d dz of d psi dz, and the right hand side will be going in the same format. I am putting the same limit, but ultimately obviously the limit of the right hand side should be 0 to psi, because it will be a psi function variation. I will come a little bit later on. And once I am putting these values, so once I am changing these values of d psi dz, multiplying both sides. So people generally argue that why you are putting the right side as d psi dz, because I have to multiply both sides by d psi dz. So intentionally I put d psi dz in as a limiting function, and once I am removing the dz part from the right side, then I can write, okay fine, now it will be as a variation of the only potential, not the derivative of the potential. So that part you have to remember more clearly. And what I am making the left part, it will be 2 of d psi dz. So if I cancel dz from both the sides, what it will be? The first left hand side, it will be electric field square, and right hand side, if you integrate it, it will be a variation of d psi. So if you integrate it, it will be a value of this expression. So this will be your expression of the electric field, where you will find two terms in the bracket, exponential minus q psi by kt plus q psi by kt minus 1, and ni square by n square exponential q psi by kt minus q psi by kt minus 1. So these are the terminologies you have to deal with later on, and will multiplied by some constant, which is nothing but the square of the electric field. Now I am coming to the square of the electric field expression. So ultimate your objective is calculate electric field and charge. So we have all the expression of electric field. So what are the boundary conditions? Naturally at the interface, if psi becomes psi s, then electric field become electric field of surface. So surface electric field is given, just replace psi by psi s, and that's the final expression. I have taken the root over, because instead of square of the electric field, I have calculated the actual electric field value. So that gives the ultimate foundation of electric field variation. So once you have this electric field variation, and you have to calculate the charge. Now the question is how charge can be calculated. That's very simple. You have to apply the Gauss's law. So for surface charge, Gauss's law is minus epsilon into electric field. Why minus? Because you are considering the minority carrier, so naturally it will be minus electrons. So naturally if you put the values of this epsilon into Es, so it will become Na will come. There may be a sign of plus minus if somebody can put, somebody may put, may not put, it may be a mod, but whatever, because that doesn't matter. End of the day, you have to plot the value of charge. So plus minus doesn't matter to all of us end of the day, because you are taking the modulus value of the charge. So you can may put, may not put. For mathematical accuracy, you may put a plus minus. For actual derivation, you may consider, okay, fine, I am neglecting that factor, I am just considering about the total expression of the charge, surface charge. So once you are getting surface charge, now we have to graphically represent the charge profile. Now I will incorporate another condition. Please think about now more details. In accumulation, band bends upwards, everybody is clear. In depletion, band bend downwards. So if one band which is bended upwards wants to bend downwards, then at a particular bias it will become flat. Naturally, from upward bending to downward bending, at a particular condition the band will become flat. So if the band becomes flat, that condition is known as flat band condition. Again, I am repeating, if bands become flat, like all the bands like in the bulk region, if the interface band is like the region of the bulk in some presence of bias, that condition is known as flat band condition. And what is flat band? Naturally, surface potential is zero, there will be no bending. And if surface potential is zero, there will be no charge. Why Qs equals to zero? If you look out the expression in the last slide, if you put psi s equals to 0, then you will get Qs equals to 0. So I am going this thing once again. So if Qs is 0, please try to plot psi s versus Qs. And naturally, it will be a value where psi s and Qs is 0. Now at that point, you may wonder why I am not taking the point in the origin, because already I have mentioned in accumulation, the potential is negative. In depletion and inversion, the surface potential is positive. So I can't consider the origin as the 0, then all the surface potential becomes positive. That is never possible. So my 0 point will be at any point on the axis whose left side will be negative and right side will be positive. Generally, our convention is take the origin as 0, but that is not possible in a particular case. Now I am going to the case number 2, which is nothing but the accumulation condition. And in accumulation condition, psi s is less than 0. If you put and make some approximation, then Qs proportional to exponential minus Q psi s by 2 kt. Why the 2 factor comes? Because it is a square root, so ultimately the 2 factor comes in the denominator. Now, I am showing the previous diagram, which is the flat band. Now, if you plot Qs versus psi s within this e to the power minus function, this will be the accumulation band bending. Naturally, it has a highest value if you go more negative surface potential, but if you comes towards the flat band condition, naturally the surface potential has to become 0 and the corresponding charge, so it will meet the axis. So that's the Venn diagram for the accumulation condition. Next, I am moving towards the case number 3, which is nothing but my depletion condition. And what is depletion condition? It will be the surface potential greater than 0 but small. So if it is small, then Q is proportional to root over of psi s. Now please, this is the surface potential, this is Qs, next comes to flat band point, next comes to accumulation. Now if you plot Qs proportional to root over psi s, that is the orange line. So this is known as the depletion criteria, where it just starts to increase but not increases very much. Why? Because psi s is greater than 0 but small. Actually, if applied voltage is small, then the corresponding surface potential becomes also small, and that is represented by this band diagram. So this is my case number 3. Now I am coming to the last case, which is my case number 4. And what is that? That will be inversion condition. And what is inversion condition? Naturally, if Vm is large, then psi s is greater than 0 and large, and Q is proportional to exponential Q psi s by 2 kt. Now, how the inversion will be plotted? If you plot this exponential function, again I am repeating, this is flat band, next comes to the accumulation, next comes to the depletion, and now if you add inversion, it will be like this. So that will be the complete Q psi profile, that means charge potential profile for a MOS capacitor, where The blue point on the x-axis denotes the flat band condition. The violet graph at the left side denotes the accumulation condition. The orange graph denotes the depletion criteria, and the rest of the green graph denotes the condition for inversion. Now you may recall at my beginning of the lecture I have said that you have to differentiate between strong and weak inversion. These are the two types of inversion. So let's come to the more detailed representation of the charge profile. Again I am drawing surface potential, charge, flat band. So this is accumulation, this is depletion, this is inversion. Fine. Now this dotted line, this is a hypothetical vertical line drawing from flat band parallel to QS axis. So what it does mean? This portion will be represented by accumulation condition. Again, the orange portion, I am drawing another parallel vertical line. So this is also parallel to QS axis. That gap from flat band to depletion, that is known as depletion condition. I am drawing another vertical line parallel to QS axis. A part where in the inversion condition graph increases but not at a very high rate. So that means it crosses the point of inversion but not at a very high rate, means this is the weak inversion condition. And the last part where the graph increases rapidly, naturally it will be the strong inversion condition. So we are now giving 5 different nomenclatures. Please think: flat band, accumulation, depletion, weak inversion, strong inversion. So all the 5 points are designated, and the green point, it denotes the transition from or depletion to weak inversion. That means the distance between flat band point to point of inversion, and that should be obviously known as psi f, that is the Fermi potential. So the distance between flat band to point of inversion, that is the psi f, because that is the bending of the band when intrinsic Fermi level touches the extrinsic Fermi level. Again, if you measure the total width of the weak inversion, it is the distance between point of inversion to the transition of inversion. What is the transition of inversion? It is transition between weak to strong. So that value will also be known as psi f. Naturally, I have said that at a weak strong inversion means psi f surface potential greater than twice of Fermi potential, or at least equals to twice of Fermi potential. So both are psi f. Now you know how 2 psi f means. 2 psi f means it is the distance between flat band point to the transition of inversion. That's a very critical aspect. Once I will start the next day the inversion approximation and depletion approximation, I will start from these points. So once you are getting this, that will give a complete Q psi characteristics of a MOS capacitor, and all these derivations with some fundamental steps and the concepts you can find out from the famous textbook of Tor and Ring. If you search in Google, there are so many beautiful publications of the Tor, single author publications in IEEE transactions, and you will find in 2000 onwards there will be several series of publications where Tor showed the variations of the MOSFET, the double gate MOSFET introduction, and later Ortiz Condre and other people has developed the model so far. But the Tor is the phenomenal fundamental publications, and his book is extremely essential. So if anyone interested to go into more details, please consult that book. Thank you all. So in the next lecture I will go to the depletion inversion approximation, then the MOS capacitance, and I will try to go for the what is the amount of charge stored for depletion and inversion condition. So thank you all for today, and you will wait for the lecture 3, that will be the third lecture of the series of MOS capacitor. Thank you all.